Hello.
Hello.
Hello, can you hear me? Am I audible?
Yeah, I can hear you.
Oh, how are you, Anya?
I'm good.
Okay. Okay, let's just begin. Let me just start sharing my screen.
Okay.
Let me know when it's up.
It's shared.
No. Okay, so Adanya, is that correct? Am I pronouncing your name correctly?
Yeah.
Okay, cool. So my name is Moaz Aruj. I've been teaching mathematics for uh, around one and a half to 2 years now, and I have academically, I have a background in accountancy and finance with the majors in finance and minors in mathematics. And I'm also a part qualified ACCA. I have one more exam to take. So the IGCSE extended mathematics. Let me ask you a little bit about your familiarity with the subject. How good are you? What sort of grade are you expecting? What sort of hopes you have with the subject?
Honestly, like I had a problem with one of the lessons, which is chapter, I think, mensuration. I had
Okay.
I had a really big problem with that.
Okay, perfect. So have you gone through the whole syllabus?
Yeah, we reach I think chapter 4, like in schools. So I reached chapter 4.
Okay. But in this class, you do expect us to go through the whole syllabus, right?
Yeah.
Okay, sounds good. Sounds good. And you're saying that you have a problem with mensuration, the chapter which is chapter 3, I think, in the book relates to circles and chords and areas and
Yes.
graphs, stuff like that, right?
Yeah.
Okay. That's good. Okay, so let me discuss how we're going to take the class and what sort of agenda we have for today's class, and then we can discuss if that's the right approach, and if you're on board, then we can continue. So basically, what I think would be appropriate for the class would be if we start with revising or going through all the topics from one up until the last one, which is 11th or 12th. We do all topics one by one. And after that, we will start with problem topics and we'll do targeted practice in order to, get your hand on those topics. Does that sound good? Does that approach sound
Yes.
good?
Yes, that sounds great.
Okay. Okay, perfect. Perfect. So the first chapter that you, okay. So the first chapter that we have here is the chapter for numbers. And we'll quickly go through this, and it would be good if you can keep a notebook with you so that you can keep making the notes and keep writing about the stuff and solving questions when they're put in front of you. And please let me know if you get stuck anywhere, if the pace is too fast for you. You can stop me anywhere in the middle. That's no issue at all.
Okay.
Okay, just give me 1 second. Okay. So these were the topics basically which I thought we'll be discussing in today's class. We'll start with obviously the first chapter, which is around numbers. We'll talk about what are some number types. It's good to know, how would you differentiate between a rational number or an irrational number, or what is an integer or whole number, and etc. Then we'll get into symbols and the rules, the bit math rule. Then we'll talk about multiples and factors. Then we'll talk about fractions. Then we'll talk about decimal places and significant figures. Then we'll talk about standard form. And lastly, we'll get to ratios and proportions. Now, one thing which I'd like to make clear here is that each topic with, if with ample practice, I think would require at least one or at most two classes. because obviously the volume of stuff that we have to cover can get a little bit too much for some topics. So it might take a couple classes to get through them. So I wanted to just make that clear. So let's talk about number types first. Number types. So there are various number types. We'll try to get to those which are some of the most common. So natural numbers. These are numbers. These are basically all whole numbers. Whole numbers as in 2, 3, 4, 4.5. That's not a whole number. So natural numbers are all whole numbers excluding 0. 0 is not a natural number, but every other number, every other whole number would be a natural number. Then very basic odd numbers. You know what odd and even numbers are, right? Or do we need to get
Yes.
into that? Okay, perfect. So basically, we'll just write this numbers which are not divisible by 2. Not divisible by 2. Not completely divisible, in fact. Like with the remainder of 0. Not completely divisible by 2. Examples could be like, for example, 5 by 2. You will have a remainder of 1 when you divide that. So it's an odd number. Then obviously, you have the opposite of odd number, which are even numbers. These numbers are divisible by 2, entirely divisible by 2. Examples could be, 6, for example. 6 by 2 gives you the exact answer of 3 with 0 remainder. So that would be an even number. Integers. Integers would include any positive or negative whole number, including 0. So basically, the difference between natural numbers and integers is that natural numbers exclude 0 and integers, they include zeros. Nothing else. Then another important number type is prime numbers. So what sort of idea do you have about prime numbers? What do you think they are?
Prime numbers?
Yep. If you don't know, you can just let me know. That's not an issue.
Yeah, I don't know the prime numbers.
Okay, cool. That's no issue at all. So basically, prime numbers are any number is a prime number greater than 1, any number greater than 1, which can be divided only by 1 and itself. So let's just get to a few examples. So basically, when we talk about prime numbers, the opposite of prime numbers is composite numbers. What are composite numbers? Composite numbers are obviously numbers which have more than 2 dividers. For example, if we talk about the number 10, right? Now 10 is completely divisible by 1. 1 times 10 is equal to 10. It is also completely divisible by 2. 2 times 5 is equal to 10. It is also completely divisible by 5. 5 times 2 is equal to 10. And it is also completely divisible by its own self, which is 10. 10 times 1 is equal to 10. Now we can look at this and we can see that 10 is completely divisible by 1, 2, 5, and its own self, 10. For prime numbers, you will see that when we divide these prime numbers, they will only be fully divisible by 1 and its own self and nothing else. For example, the number, this is a composite number. A prime number's example would be 7, right? Now 7, if you think about it, 7, 1, obviously 1 times 7 is 7. But 2, 3, 4, 5, and 6, none of these numbers can be multiplied with any number to get 7. The only other option is 7 times 1 is equal to 7. So numbers which have only 2 dividers are prime numbers, 1 and their own self. And 7 is an example. 5 is an example. Say 5, the only 2 factors for 5 are 1 and 5. 11 is an example. The only 2 factors for 11 are 1 and 11. Is that making sense? Are you getting the point?
Yeah.
Okay. So it's clear now, right? What is the difference between prime number and composite number? If it comes in paper, you'll know.
So prime number, if it has only 2 dividers,
yeah,
which is like example 7, 1 times 7 is 7 times 1.
right.
And then composition number is like, as the example, as you said, 10, which can be multiplied by 3 numbers.
3 or more numbers, yeah.
Yes.
Could be, 10 numbers. But all that will fall into the category of composite numbers. Prime numbers will always have just 2 dividers, and one of them will always be 1, and the other one will always be the number itself. For example, let's take the example of 23. 23 is also a prime number. Any number below 23 cannot be divided. Cannot divide 23 fully. There won't be a remainder of 0. So 23 is also a prime number, and it only can be divided by 2 numbers, which is 1 and 23. I think 71 is not a prime number. Another prime number is 19. 19 is also prime number. So yeah, is that clear?
Yeah, it's very clear.
Okay, perfect. Okay, so the next step is knowing about rational and irrational numbers. What sort of idea, if any, do you have about rational numbers or irrational numbers?
Rational numbers are they like whole numbers, like regular numbers?
No. So basically, the rational numbers are numbers in which the solution of those numbers, I'll just give you, when I give you the examples, you will get to understand it a bit more, a lot more clearer. But these are basically numbers which have terminating or repeating decimals. What do I mean by that? Let me just first write this so that it's fixated in your memory. Numbers with terminating or repeating decimals, and irrational numbers. Irrational numbers. Numbers with non-terminating or non-repeating decimals. Now let's look at a few examples. For example, the number 6 itself. If you see this number, there are no decimals, right? Or if you were to put a decimal, you write it as 6.0. But that's it. It's not repeating. It's just this. This would be a rational number. And for example, if you see 8 by 2 written somewhere, you know that this number is basically simplified to become 4. This would also be a rational number, non-repeating decimals. If we were to put a decimal, you'll write it as 4.0. That's it. But let's talk about numbers like, for example, which number can we take? Not 3, 5, 2, not 5, 5, 2, 6, 7, 9, 2. Irrational number, for example, have you heard of pi?
Yes, which is 3.14.
Yeah. But it's not 3.14, this is an irrational number.
Okay.
Irrational number. The exact value of pi is calculated by 22 upon 7. And if you were to calculate this value in your calculator, and let me just do this right now, the number goes something like this: 3.142855714. And this just keeps on going ahead. It never stops. The pattern never repeats. After 1 4, then it's
Irrational.
yeah. So it just keeps on going. It doesn't stop. Like, for example, this is 22 by 7, which is an irrational number. But if we take 5 by 2, right, and if we divide this, we will get 2 times 2 is 4. We'll get a 1 down here. As a reminder, we'll put a point here. We'll get a 0 here. And then 2 times 5 is equal to 10. And the remainder is 0. So the decimals have stopped just after one place. So 5 by 2, which is 2.5, is a rational number. You see how the decimal has stopped? For pi, it never stops. It just keeps on
Yes.
moving.
Yes.
So that's the thing. You basically need to hold on to the concept of rational and irrational numbers. It's not like you're going to use it in theory or in questions. Sometimes you might be asked some questions about rational or irrational numbers, but most of that would be related to the theory, knowing the theory itself. So what is the difference? So you just need to know that rational numbers are numbers which with terminating or repeating decimals, where the decimal places are ending, and irrational numbers are basically those numbers where the answer just continues. It continues on and on and on. It never stops. Does that make sense?
Yes.
Perfect. So how basically will are you taking the notes?
Yeah, I'm
for these
taking the
things?
notes.
Okay, so how we're going to basically do this is that we have a gap in our classes, right? We have one class today, and then
Yeah.
our other class would be on Thursday, right? So you
Yeah.
will have Wednesday to do whatever you want to do. What I would highly suggest is going through your notes one more time, and then trying to solve the questions from the book. We'll get to the questions as well in the class. We'll try to do as many as we can, but as much as you can do at your home, your skills are going to get polished, right?
Yeah.
So I would highly suggest you go through the lecture once more, and then you try to do the questions inside the book. And if you come up with any confusion, you can reach out to me over on WhatsApp. You can reach out to me in the class itself, and we can discuss your problems.
Okay.
So that's no issue whatsoever. So okay, so this was all when it comes to number types. Let's see what other thing we had on our agenda. This is done. We had symbols and mass rule. Okay, so this is very basic, very basic, but I just need to make sure that you know this. Symbols. Please excuse my writing. And mass rule. So what I mean by symbols is basically just these things: the sign of greater than, the sign of less than, the sign of greater than and equal to, the sign of less than and equal to, square root, cube root. And do you know these signs? Do these look familiar to you?
Yeah.
Okay, so when you see an expression like this, x is, for example, greater than 10. So what do you think are the possible values of x? If this is true, if x is greater than 10, then can x be equal to 8? What do you think?
No.
No. Why not? Because x is greater than 10. It has to be greater than 10. How about, can x be equal to 21? If x is always going to be greater than 10, can it equal 21?
Yes.
Yes, simple and straight. How about if you've given a condition like y is less than 12? Now, you see this expression, y is equal to, for example, 13. And the examiner asks you, would this be true or false? What would you say?
False.
False. And why is that?
Because it's less than.
Yeah, y has to be less than 12. You see these signs, basically whenever the shape of the bracket is open towards the thing, that means that the symbol or the number where the bracket face is open, that will be greater. And where it is closed, where it is the pointy edge, this will be smaller or lesser, right? So y,
Yes.
these pointy edges towards y, then that means that y is less than 12. If this is the rule, then this is false. However, if y is less than 12 and you see this, y is equal to 10, then that would be true because you understand that y is less than 12. If y is equal to 10, then that satisfies your condition. 10 is less than 12, y is less than 12, 10 is less than 12. If y is equal to 10, then the condition satisfies. Does that make sense?
Yes.
Perfect, perfect. Okay, now let's talk about, okay, so let's take one more example. X, or let's just say A, is greater than 25. See, the open face is towards A, which means this is greater than, A is greater than 25. Okay, now you see this written, A is equal to 10, for example. Would this be correct or would this be wrong?
The wrong one is A equals 10.
Absolutely, because this is the condition and this does not satisfy the condition. If I write A is, for example, equal to 27, how about now?
Yes.
Then this is correct, absolutely right. However, tell me, would this be correct or would this be incorrect? A is equal to 25. Is this correct or is this incorrect? What do you think?
Yes.
You think this is correct? No, this is not correct. This is incorrect. Let me tell you why. So this sign is telling you that every value A can be any value. A can be equal to any value as long as it is greater than 25. It has to be greater than 25, right? It has to be. It cannot be 25. It has to be greater than 25. But
So
there are cases.
if we get a question that is like A equals the same number, it's incorrect.
Yep. It will be incorrect 100% of the times. However, there is one thing which you need to understand. There are two other signs, and those signs are called greater than equal to and less than equal to. Let's do a few examples for these. For example, the same question was asked. A is greater than, but now the sign is like this, and then 25. Now in this case, what this mathematical expression is translating to is that A is greater than
25.
or, no.
Oh.
See, the sign is different, or equal to 25. This is different than, this is different than this sign, which suggests that A is greater than 25. You're getting the difference? When there is a little line underneath the sign, whether it is a greater
The
than
only
sign or a
difference is
lesser
just
sign,
the line underneath.
just the little line, which is why you have to be super conscious. If you miss this, then you've ruined the question. So you need to be super conscious that is it a greater than sign or is it a greater than equal to sign? greater than or equal to sign.
Okay.
So yeah, so let's just do a few examples of this again. Now, for example, again, let's take this one. You have the condition which is telling you that A is greater than or equal to 25. And the examiner asks you that according to this particular condition, would this be true or false? What would you say to him?
Yes.
This would be true. Perfect. However, again, if they ask you about this, A is equal to 24, according to this condition, would this be true or false then?
False.
It will be false, because obviously A has to be greater than or equal to 25. If A is equal to 24, then obviously it is false. The same goes for the less than sign. If A is less than 25, or A is less than or equal to 25. So if A is less than 25, then A can never be equal to, so this is actually the sign of not equal to, can never be equal to 25. A has to be less than 25. So A can be equal to 18, for example, 24, for example, or 0, or even -1. But A can never be, yeah, A has to be, A can never be greater than 25. Does that make sense? This was fine.
Yes.
However, if you have this sign, A is less than or equal to 25. So in this particular case, A can be equal to, which is clearly. So in this particular case, A can definitely be equal to 25. This will be true. And A can be equal to 24. It can be equal to 0. A can be equal to -25. A can be equal to -100. Is this making sense?
Yes.
Perfect. So we are through with the greater than sign. We are through with the less than sign. We're through with the greater than or equal to sign. We're through with the less than or equal to sign. You already understand the equal to sign. And another sign that we discussed is the not equal to sign. Now let's talk about squares and cubes. Any idea around these? What are squares and what are cubes?
Yeah.
Okay. Tell me what a square is.
Square is it's like double the number or something. Wait.
No, not double the number. Okay, I get it. Okay, I'll just explain once. You don't double the number. That is the wrong way to think about this. The way you need to think about square, let me just write this as well. Squares. So square is basically multiplying the base number by itself once. And this once needs to be highlighted, right? And let us just first write the definitions and then we can get to the examples. Cubes. You will understand this more clearly when we do the indices topic, but it's paramount that we understand at least squares and cubes prior to continuing with the course. Multiplying the base number by itself twice. Okay, so let's get into some examples. For example, you see this written somewhere. For example, I ask you, tell me the square of 2. Now, according to what we wrote above, the square means multiplying the base number by itself just once. The base number, base I've written, and we'll get to the why I've written base here in a while. But base number, you can just ignore this base for now. Multiplying the number by itself once, right? So the
Yes.
square of 2 would be 2 times 2. which is equal to 4, right? The square of 7 would be 7 times 7. You multiply 7
49.
by itself, which would be 49. Perfect. How about the square of 10? What do you think that would be?
100.
Yeah, you will do 10 times 10, which would be 100. Okay, perfect. Now, let's talk about cubes. These are examples. Let's talk about cubes. How about the cube of 2? Now, what do you think that would be? The cube of 2.
4.
No. You see, the definition for the square was multiplying the number by itself one time, once. For cube, it is twice. You multiply the same number
So it's 8.
by itself, it would be 8. Perfect. 2 times 2 times 2. It's better to write this, you know, in your initial phase. So once you get through half the course, then you'll be able to do this in your head. But it's better to write this so that you train your brain, how you picturize all of this in your brain when you do that later on. So 2 times 2 times 2, that would be 8. How about the cube of 5? So we'll write that as 5 times 5 times 5, which would be 125,
5.
right? And how about the cube of 10? What would that be? The cube of 10.
Okay. 110.
No, the cube of 10. Think through that once. What should I write here? First of all,
10
I need to
times
write.
10. 10
Absolutely.
times 10 times 10.
Exactly. So 10 times 10 is, what is 10 times
100.
10? And 100 times 10 is? You just add a 0 at the end, right?
Yes.
So that's 1000.
Oh, okay.
1000, right?
Yeah.
So that's pretty much it about squares and about cubes. Now, one other thing that we need to understand about the square of 2. So basically, a lot of this stuff, Dania, that you will see in any mathematics course is converting the English language into mathematical expressions. You see, you will be given questions sometimes in the English language, as we will see as we move down, further into this course. So one of the main tasks is for you to be easily able to convert the English language into mathematical expressions. For example, right here, when I write the square of 2, so this can also be written as 2 raised to the power of 2. When I write the cube of 2, this can also be written as 2 to the power of 3. This little thing translates into 2 times 2, and this translates into 2 times 2 times 2. Is this making sense?
Yes.
Right. The cube of 2, the square of 2. When we talk about indices, you will see that this little number that we write here on the top can go up to 10 or 100 or 1000. Now that doesn't mean that you multiply 2 by 1000, because we just understood in the previous definitions that we wrote for cube, that whenever you have a power, this is called a power or an index. And
Yeah.
which is why I told you that we'll learn more about this when we learn indices, right? So this little thing, this little number that's at the top, this 2, this 3, these are powers. And another way to say that to say this particular phrase, the square of 2, can be 2 raised to the power of 2. So if you see this written somewhere, this is basically just 2 raised to the power of 2. It literally means that 2 is raised to the power of 2. It can also be written like 10 raised to the power of 5, for example, right? So you will convert this sentence into 10, and then you will raise it to the power of 5. Now, as we've done this before, you will understand that this doesn't mean that you multiply 10 by 5. No, that's absolutely wrong. What you will do is you will write 10 5 times. And you will multiply 10 5 times with each other. And you will get to 1, 2, 3, 4. Right?
Yes.
So this is all about it. We've actually done 30%, 35% of indices here as well. So basically, what I wanted you to understand from this was get a pretty good hand over the squares and the cubes. And I think, do you have any confusion in that? Or are you good?
Yes.
Okay, okay, good. So this was the second thing on my agenda. We're done with symbols. Okay, the bitmess rule. The bitmess rule is pretty simple. I think it's a little bit premature to get to this. We'll start this later. Let's start this here. Bitmess is remaining. We'll get to this later. Okay, multiples and factors. Any idea what multiples are? Any idea what factors are?
Multiples.
Multiples and factors. So if you don't have any idea, that's not an issue whatsoever. It's a very, very basic thing. Multiples are extremely basic. Factors are also extremely basic. And you just let me know if you
Multiples are
if
like
you know.
the multiples of like 12. Like
Yeah, what would be those, the multiples of 12?
12,
Mm-hmm.
24,
Absolutely, perfectly.
36 to 48.
And so on, right? They can go into infinity. They never stop.
Yes. And factors is like
Yep.
like the factors of 12, like what do you multiply, like two numbers that you can multiply to get 12.
To get to 12.
Yeah.
Absolutely. So I don't think we need to spend much time on this because I just wanted you to have the idea of what multiples and factors are. So, okay, let's just write a little bit of definitions so that we can go through them if you're ever confused. So multiples are calculated by multiplying a number with positive integers. Okay, so any number, for example, 5, or for example, we took the example of 12. What are integers, Sania? We talked about integers in the class. Do you remember what integers are?
Yes. They are like
In,
positive and negative numbers.
yeah, including 0 or excluding 0?
Excluding 0.
No, they include 0.
Okay.
Integers will include 0. Natural numbers and integers are the same, but the only difference is that they don't include 0. Natural numbers exclude 0, integers include 0.
Yes. Okay.
Okay. So any positive, but what we know about 0 is neither positive nor negative, right? It is a neutral number. If we go back from 0, -1, -2, -7, blah, 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 there would be negative numbers ahead of 0, 1, 2, 3. Those are positive numbers. 0 is a neutral number. So what we're talking about when talking about multiples is that multiples are calculated by multiplying a number with positive integers. That would mean integers which are ahead of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So when we talk about 12, 12 times 1 would be 12. So 12 is a multiple. 12 is a multiple. 12 times 2 is 24, then 36, 48, 60, 72, 84, and so on. You already know this.
Yes.
Okay. And so this would be the last thing that we do. Then we'll practice some fractions for today. And after fractions, yeah, I think the rest of it we can continue in the next class. But one last thing that I would like to touch upon in this one is the concept of, it is the concept of lowest common multiple. Okay. Daniel, what do you have any idea, any understanding? Does this mean anything to you, which is also known as LCM?
Yes.
Okay, good. Please tell me.
Lowest common multiple is like if two numbers have the same low number, like as if like example, if the both numbers have the number 2, like
Yeah, let me just navigate it a little bit for you. You are almost hitting it perfectly on the head, but not entirely. And so basically, we're talking about multiples here, right? For any two numbers, what are their common multiples? The smallest common multiples, right? The smallest
yes.
common multiple, that would be the lowest common multiple. Let us just first write the definition, not the definition, just something that you can get back to when you're confused about this. Let me just write that, and then we'll look into so many examples. And I'll also, okay, I'll get to that later. LCM of two or more numbers is the lowest, this has to be highlighted, lowest number which is a multiple again has to be highlighted of all the given numbers, right? So let's just take an example. For example, we take the example of 5 and 8. So you have these two numbers, right?
Yes.
Let's just write the multiples of 5 first. In fact, let's just write with 5. So the multiples of 5 would be, can you please tell me what the multiples for 5 would be?
1 and 5.
Yep, 5. After that,
there's no other number.
no, multiples. You see, multiples.
Oh yeah.
Yeah, not factors,
5,
multiples.
5, 10.
Yep.
15.
Just keep going. I'll stop you. Yeah.
25.
20, then 25.
Yeah, 20,
yep.
25, 30.
Yep.
35.
Yeah. 2 more.
40 and 45.
Yeah. Perfect. And how about 8? Can you give me a few multiples of 8 as well?
8.
Yep.
16.
Yes.
21.
24.
24. 28.
Yep. 24, then you will have 32. You just add 8 to 24, you get to 32.
Okay.
And the fifth one would be after 32?
32, 40.
40. And one more, just one last. What would be another one? 48. Perfect. Okay. So now you have the multiples of 5 and you have the multiples of 8. And the question was, find the LCM of 5 and 8. So this was the question put in front of you. So what you did was you wrote the sum of the multiples of 5, then you wrote some of the multiples of 8. What you're looking for is the common number that is in both the multiples. So where do you think that is happening? What is the
40.
commonality? 40. Yes. So this is the first time that a commonality is there. There would be other commonalities as well. For example, when you get to, okay, let's just take that as well. 48, then you get to 56, then you get to 64, then 72, then 80. And here you have 50, then you have 55, then 60, then you have 65, 70, 75, and lastly you have 80. You see now,
Yeah.
you also have another commonality here. But well, look at what the words suggest. First, look at
LCM.
M. Yeah, you've
Yeah.
got the multiples, then you look at common. You got two pair of common multiples, 80 and 40s, but you need to get the lowest one. So you take the 40.
Yes.
So it's that basic. It is extremely basic. And I also tell you a way to do this very quickly. And I don't know if you already know this, but it would come in so handy and it will make you so quick if you learn this method. Like for example, you were asked to get the LCM of 5 and 8. So what you need to do is write 5, and then you need to put a comma, and then you need to write 8. And then you need to make a design like this, right?
Yeah.
Now what you need to do is you need to start from the lowest number after 1. What is the lowest number after 1? That's 2, right?
Yes.
Greater than 1, the lowest number is 2. You need to see that either of these two will have 2 as a factor. 8 will have 2 as a factor, right? You write 2 here. 5 does not have 2 as a factor. You write 5 down here as it is. But 8 has 2 as a factor. 2 times 4 equals 8, right? So you will write 4 here. You'll draw a line. Then underneath that, again, you will use 2 one more time because one of these numbers has 2 as a factor. 5 does not have 2 as a factor, but 4 does. You will write 2 again, 5, comma, 2 this time, because 2 times 2 is 4. Now, again, 2 has 2 as a factor. You will write 2 here again, but 5 does not, comma, then 1. So you need to get both ones, but 1 is 5. Now for 5, 2 is not a factor of 5, 3 is not a factor of 5, 4 is not a factor of 5. Is 5 a factor of 5? 5 is a factor of 5. So you'll write 5 here. You have to start from the lowest possibility. You start from 2, you get to 3, 4, 5, 6, 7, and so on. So 5 times 1 equals 5, comma 1. And that's it. Now what you need to do is, this is your answer. 3 2s and 1 5. You will write it like 2 times 2 times 2 times 5. So 2 times 2 is 4. 4 times 2 is 8. And 8 times 5 is 40. So the lowest common multiple of 5 and 8 would be 40, as we did it from this long method here as well. You see 40. So have you ever done it through this method, the one that I just showed you?
No, we did the long method.
The long method. But this is the short method, and this will come in very handy for you. At even, in cases when you even have to check your answer, you can do this in like 10 seconds for any number. Like for example, you have got, is it clear? I will do a few more examples, but is this one clear?
Yeah, very clear.
Okay, perfect. Now let's just take another example of, you get the question that you need to find the LCM of, for example, let's just take 10 and 14, right?
Yes.
So again, what you will do is you will write 10 here, comma, and then you will write 14, and you will make this. Now what you will see is you have to start from 2. Always start from 2. And you see that 2 is divisible by both these. So you write 2 here. You know that 2 times 5 is equal to 10. You will write 5 here, comma. And you know that 2 times 7 is equal to 14. You will write 7 here. You will draw a line. Now 5 has only 2 factors, 1 and 5. And 7 also has only 2 factors, 1 and 7. So that means that these are both prime numbers. Only two factors. And 10 and 14 have more than two factors, so those are composite numbers, but this is just, something to reiterate. As they are prime numbers, obviously they won't be divisible by any number other than one in their own self. We cannot take one as we discussed here, so we will take 5. We'll write 5 times 1 equals 5, comma, 7 will get down as it is because 7 is not divisible by 5. Then we'll take 7, 1, comma, 1. Now the LCM for this would be 2 times 5 times 7, which is 70. 2 times 5 is 10. 10 times 7 is 70. Is this clear?
Yes.
Okay. How about we do 2, comma, 6. We draw these lines. Again, we have to start from 2, and we'll see because 2 works as well. 6 is also divisible by 2, and we see 2 here, so we can write 2 here without any hesitation. 2 times 1 equals 2, and 2 times 3 equals 6. Now, obviously, 3 is not divisible by 2, 3 is divisible by 3. So we'll write 3, 1, comma, 1. The LCM of 2 and 6 would be 2 times 3, which is 6. And also, as 3 is not divisible by any number other than 1 and its own self, this is also a prime number. So no, it's good if you train your mind to see these sort of patterns and these sort of things when you're doing mathematics. I just want in the back of your head, right? That you see 3 here. Oh, okay, so 3, your mind just goes, okay, so 3 is a prime number because 3 is only divisible by the number itself, which is 3, and 1. So that would mean that we cannot write any other number here other than 3 to divide it. Does that make sense, or is it getting too much?
No, it's very simple.
Oh, okay. That's wonderful to know. Okay. So, Daniel, what I would do is I would give you around 10 to 15 questions of these LCM type things, right? Where you will need to calculate the LCMs using this method, the one that I've shown you here. Would that be okay, or would it be too much to do over the next
No, it's
almost
fine.
2 days?
It's fine.
It's fine. Oh, perfect. So I'll share that in the WhatsApp group. Okay.
Okay.
Later on, after the class, I'll share those questions in the WhatsApp group. How much time okay, we have around 8 to 10 minutes left. Anya, just let me know how good you are with fractions. Do you understand them? Do you know how you subtract them, add them? Fractions, do you know what these are in the first place? Fractions.
Yeah, I know fractions.
Okay. And how good are you with, multiplying them or dividing them, fractions with each other?
Oh, like when they ask to divide the
Like
fraction.
for example, you get a question like this: 1 divided by 3 times 4 divided by 7. Do you know how we would go about this question?
We multiply like
Yep.
we change the denominator first.
Okay, what we would do with the denominator, sorry?
Do we change them or do
No.
we keep them
Okay,
the
so
same?
so it's better if we get to the rules first. We'll do multiply and division now because addition and subtraction would require you to be very, very handy with LCMs. Okay, so we'll
Okay.
do addition and subtraction in our next class when we do get handy with LCMs. Prior to that, we can get to division and multiplication because it's rather easy because it doesn't require you to take LCMs. Okay, so for example, this particular question, it is very basic, Dania. What you need to do is you just need to multiply the numbers which are right in front of each other. The numerator with the numerator, the denominator with the denominator, and you will have your answer. Nothing more serious than that. So you will do 1 times 4 divided by 3 times 7, and you will have 4 divided by 21. That's your answer. You get, for example, you get 7 by 9 times 12 by, I don't know, 13 or 15, for example, right? So this would be 12 times 7 times 12, or 12 times 7 means the same thing, and 9 times 15. So your answer would be 84. 12 times 7 is 84, and 15 times 9 is 135. Do you get the idea? It's very basic. You just multiply the
Yeah,
numerator
but
with the numerator
okay.
and the denominator. Any question, any confusion?
Yeah, I have a question.
Yeah, please go
So
ahead.
84 divided by 135, do we simplify it or keep it the same?
Yeah, okay. So I was just trying to teach you the methodology of multiplication of fractions, right?
Yes.
We have to simplify the fractions as much as we can before handing them off as answers. Yeah, this is, just remember this, always, this will always be the case. Simplify the fraction as much as possible before you give it as an answer. Like for example, if we look at this step only, okay, let's go through this as well. 7 by 9 times 12 by 15. So we understand that this fraction, 12 by 15, can be simplified, right? How do you think this will be simplified, 12 by 15?
Twelve by 15.
Yeah.
We divided by 5.
You see, what I would highly suggest here is that if you need to look at factors, right?
Okay, yeah.
For example, you see that which is the least number, the lowest number that both these numbers are divisible by, right? For example,
Yes.
2, we take the 2 as the lowest number that both these numbers are divisible by. 12 is divisible by 2, right? 2 times 6 is 12, but 15 is not divisible by 2. 2
Yes.
times 7 is 14, and 2 times 8 is 16. There is no 15, right? How about 3? If we talk about 3, then 12 is divisible by 3. 12 times 3 times 4 is 12.
Yes.
And 15 is also divisible by 3 times 3 times 5 is 15. So all you need to do is divide both these, the numerator by 3 and the denominator by 3. And you will get to 4 times 4 over 5.
Okay.
Does that make sense?
Yes.
Right? Whenever you're multiplying, it's better to simplify first and then multiply rather than multiplying and then simplifying, because you get to practice a lot more. You can do any way you want in the exams, but it's better to do it like this when you're doing fractions. Now, when you're doing it in class or even in your exams, if you are crushed for time, then you can do it later on. But it's a lot easier because the numbers are smaller to do it in the first steps. But this is only when you're multiplying and dividing.
Okay.
Does that make sense?
Yes.
So the multiplication, is that clear? The multiplication aspect of this?
Yeah, it's very clear.
Perfect. So Danya, we are running out of time. What I would suggest you to do is go through all of this. You would have taken notes. You go through all of this again. And then what you will do is I will share with you in about a couple of hours some questions which will relate to LCMs, which will relate to multiplication of factors, and they won't be relating to division of fractions, because obviously we have not completed that. And the LCM questions, I would highly suggest you do it from this method, not from the longer method.
Yes.
Okay. And what else did we go through today? Okay, I might give you a few questions of indices as well. And hopefully it won't be too much. And if it is too much, then you can let me know in the next class and we can, divide the workload. That's no issue whatsoever.
Okay.
Okay.
Yes.
Okay, so any questions, any last minute thoughts, anything, you can let me know.
No questions.
Cool. Perfect. So thank you so much, Danya. We'll see you on Thursday, same time. And best of luck with the questions.
Okay, thank you.
Okay, take care. Bye-bye.
Bye.